In Steam Power Part 1, we have already looked at how a steam power cycle works, how the Rankine cycle models it, and manual solution and verification is in test calc. Here we are going to do qualitative performance prediction, discuss an ideal Rankine cycle versus an actual cycle, and modifications. Let us first recap how an ideal Rankine cycle works. Steam at a very high pressure and temperature expands through the turbine from state 1 to 2. An ideal turbine is isentropic. From 2 to 3, heat rejection takes place. Q dot out comes out here, and as heat comes out, the steam condenses from state 2 to 3 at constant temperature, because at constant pressure, and in this case also constant temperature. And from 3 to 4, the pump raises the pressure back to the boiler pressure, and from 4 to 1, constant pressure heat addition takes place. We already know that the area inside the TS plot, inside the loop, is proportional to the net work of the cycle. Also, to understand what the efficiency should be for the Rankine cycle, always an equivalent Carnot cycle analogy is very effective. For that, we have heat. We look at where the heat is added from state 4 to 1, and kind of if we think of an effective temperature of heat addition, TH bar, and an effective temperature of heat rejection, in this case it's constant, it is obviously this temperature, then the thermal efficiency of a Rankine cycle will go with this expression, equivalent Carnot efficiency. So if we can figure out in any modification of the cycle how TH bar or TC bar behaves, that will give us clue into how a particular modification affects the efficiency of a cycle. And also the net area inside the cycle will tell us if the power output of the cycle, the net power of the cycle, will be affected by that modification. Okay, so let us now see how a particular modification will affect the cycle efficiency and the net power. Suppose we ask ourselves, how will the condenser pressure affect the cycle efficiency? So in this cycle, heat addition takes place, let's call it the red cycle, from 4 to 1, and heat rejection takes place from 2 to 3. So TH bar and TC bar can be deduced from this diagram. Now suppose we reduce the condenser pressure. What effect will it have? So let's draw a lower pressure line. So if we reduce the condenser pressure, so the steam will expand to the turbine from not 1 to 2, but it will go further down isentropically to state 2 prime. But then in the condenser, the heat rejection takes place at constant pressure, we know that, so it will move to the left, and in any ideal cycle, the exit condition is such that 3 prime will be saturated. So it exits as a saturated liquid at state 3 prime, and then the pump will raise the pressure back to 4 prime. So this will be the new cycle. Suppose we use the color blue for this. The heat addition temperature takes place from here onwards to the same point, and heat rejection takes place here. So therefore, the thermal efficiency First of all, we can see the net area has already increased, so therefore the net work will be higher if the condenser pressure is reduced. On top of that, we see that TC bar is significantly reduced and TH bar is slightly reduced. I mean, if you look at it, every point of heat rejection has been lowered, whereas just a slight lower temperature is added to the heat addition temperature. So in general, TH bar is barely reduced, whereas TC bar is reduced tremendously. And you can show that therefore thermal efficiency generally goes up. And in this diagram, it seems like 4 and 3 are very separated, but actually these points are very close together. But as you solve problems, you'll realize that it is the reduction of TC bar that causes the efficiency to increase when the condenser pressure is reduced. Well, and of course the network is tremendously increased. The next question that comes in mind, if the reducing the condenser pressure is such a good thing, how low a pressure can we go to? Well, if you think about it, the heat rejection must take place in the condenser. And where do we reject heat? We reject heat to maybe in a recirculating water from a river or from the ocean or from a cooling tower. But whatever we choose, the cold temperature is basically limited by the atmospheric temperature. So if the atmospheric temperature is, let's say, 20 degrees Celsius, then the steam must be condensing at slightly higher temperature to allow for heat transfer. Let's say steam is condensing at 25 degrees Celsius. In that case, the pressure here will be decided by the saturation temperature at temperature being 25 degrees Celsius, the pressure will be P set at 25 degrees Celsius. In other words, inside the condenser, steam is condensing at 25 degrees Celsius, which means, imagine if steam condenses at 100 degrees Celsius, the pressure is 100 kPa. If it condenses at 25 degrees Celsius, the pressure might be way, way low. You can go to the pressure saturation table, temperature saturation table, and find out the pressure at which water will condense or boil at 25 degrees Celsius. It will be really low, maybe 5 or 6 kPa. So inside the condenser, the pressure is really, really low. And how low it is depends on the cold reservoir temperature. Okay, now suppose we run another what-if scenario. Suppose we ask ourselves, how will an increase in the turbine inlet temperature will affect the efficiency or the net output? Well, 1, 2, 3, 4 is the basics cycle. So if we increase the maximum temperature of the cycle, so that will mean that now suppose we heat it up to 1 prime, then to the turbine, the new cycle will be, again, isentropic, 2 prime. So it will be 4, 1 prime, 2 prime, and 3. So as you can see, the area underneath and area enclosed has increased, so net work has gone up. And what will happen to the efficiency? Eta thermal 1 minus TC bar over TH bar. As you can see, the blue line, the blue circle, has a heat addition from 4 to 1 prime, whereas the original cycle has a lower temperature. The heat rejection, on the other hand, hasn't changed. So TC bar, whereas let me use the blue color for this guy. For the blue cycle, the TC bar has increased, and for the previous one, let's call it red one, for the Reheat cycle, the base cycle, the average temperature of heat addition is a little bit lower. So therefore, as we increase the maximum temperature of heat addition from 1 to 1 prime, TH bar is going up, whereas TC bar doesn't change. This is our symbol of things not changing. So therefore, the efficiency must be increasing. So in general, in a Rankine cycle, if you increase the highest temperature of heat addition, turbine inlet temperature, the efficiency increases, as well as the net power goes up. Well, we'll come back to how to modify a Rankine cycle to improve its performance. But before that, let's take a look at an actual cycle. In an actual cycle, the turbine need not be perfectly efficient. So as you can see, the exit conditions can be given by two different states. 2 is the isentropic exit state, where there is no friction inside the turbine, no heat transfer, and 3 is the actual turbine exit. So that they are related by the turbine efficiency. The isentropic efficiency of the turbine is given by the smaller amount of work, the actual work from the turbine to the ideal work from a turbine. And of course, as you can deduce, the actual work is H1 minus H3. So if the turbine efficiency is supplied, turbine inlet temperature is known, inlet condition is known, so H1 is supplied, and H2 can be deduced from the fact that we know the exit pressure and we know the entropy between 1 and 2 are the same. So therefore, from this equation, H3 can be figured out. So just like the turbine, with the pump efficiency, you can relate the actual exit state 6 with state 4 and 5 through the pump efficiency. Okay, now let's take a look at some of the modifications we can make to the turbine, to the vapor power plant, to make it more efficient and make it produce more power. The first modification is the reheat, and what is done in reheat cycle, again there is a nice animation on reheat, is that the turbine is split into two different stages. Instead of having the entire pressure drop occur from 1 to 2 prime in an original Rankine cycle, 1, 2 prime, this is our state 1, 2 prime, 3, 6 is our original cycle. Instead of that, the turbine is broken into two parts. After the first stage of expansion, 1 to 2, the steam is rerouted through the boiler so that steam gets heated up. Again, when things get heated up, pressure doesn't change from 2 to 3, where the reheat takes place. Pressure remains constant, so this is a different constant pressure line. And we'll assume, in general, the maximum temperature is not affected. It's the same maximum temperature the steam reaches. From 3, the steam expands isentropically, state 4, and everything else is like as before. So how does reheat help? Well, first of all, as we can see, there is an extra area in the cycle, which means the W dot net will be much higher. What about the thermal efficiency? We know we can qualitatively predict it by looking at how TC bar and TH bar is affected. Obviously, TC bar is about the same, doesn't change. And this is our symbol to show nothing changes. What about TH bar? In the original cycle, heat is added from state 6 to 1. In the modified cycle, 6 to 1 remains the same. The additional heat is added from 2 to 3. So you can see that the additional heat is added at a higher temperature on the average. So effective temperature will go up. It's like, suppose in a bar there are 10 people earning certain amount of money each, and suddenly some extra people come and join them, and each of them are at the higher bracket, so average income will go up. So in that analogy, you can say that the TH bar for the cycle will have a tendency to go up because of reheat. And as you can see, as a result, the efficiency will go up. Again, numerically, it's much easier to show, and we can solve a problem and run a what-if scenario using test-calc, and you can show that reheat generally helps for a Rankine cycle. As opposed to in Brayton cycle, if you recall, if you add reheat, the TC bar also increases almost in the same manner. So therefore, in a Brayton cycle, reheat is not a sheer thing. But in a Rankine cycle, most of the time, reheat will increase efficiency as well as add extra work. Well, finally, let's discuss regeneration. As you recall from our discussion of gas turbine and Brayton cycle, regeneration means taking heat from a part of the cycle and transfer it to another part, as a result increasing the efficiency of the cycle. Now what's happening here is that the modification is very simple. Some steam is bled from in the middle of the turbine at state 2, and the condensate that's returning from the condenser is pumped up, and this bled steam is then mixed here, producing warmer water at state 6. And then a pump raises it back, another second pump will raise it back to the boiler pressure. So this heat exchanger, or this mixing chamber, which is called an open type heat exchanger or feed water heater in industrial terminology, is the regenerator. So the question can naturally be asked that we are bleeding steam from the turbine, so obviously the turbine is going to produce less power. How in the world this cycle is going to be more efficient? Well, if you fall back on the Carnot analogy, you will notice what happens. In the original cycle, heat would have been added from state 5' to 1, but because the feed water heater, because what we are doing is that the water that is going to the boiler now is preheated by some little steam extracted from the turbine. Yes, the turbine will produce less work, but because the TH bar is going up, the thermal efficiency of the Rankine cycle, as you can see from our Carnot analogy, TC bar, as you can see, doesn't change, but TH bar is going up, and as a result, the efficiency of the Rankine cycle will go up because of regeneration. It will be very interesting to solve the problem in detail with a feed water heater to show that numerically. As will be shown, I mean, you can go through different animation to see that if there is a combination of reheat and regeneration, the cycle can produce more power at higher efficiency. So we'll stop here and solve a detailed problem involving an open feed water heater, and that will bring out the meaning together. And we'll also do a parametric study that if we have an open feed water heater, we'll see how much the efficiency increases and if there is any impact on the network of the cycle.